Bismillahirrahmanirrahim. So, welcome to week 11 lecture, and the topic is chapter 5 of the book on power. Okay. So, this is the outline of the lecture. First, we will go through the basics definitions of power and energy. Then we will study dynamic power and then static power. So what is power? You know from your basic circuit analysis course that power is the current times supplied voltage. So you can say the instantaneous power P as a function of time is equal to current as a function of time multiplied by voltage as a function of time. Now energy on the other hand is the integral of instantaneous power. So for a specific amount of period of time, you sum up all the instantaneous power and you call this energy. Okay. Average power is basically energy divided by time period. So you can write it like 1 by t integral 0 to t pt dt. So this is average power. Now for different circuit elements we can write these equations. So for example, for supply voltage VDD in which a current ID flows, you can write the power of the supply PVDD as a function of time equal to IDD as a function of time multiplied by voltage, which has a fixed value VDD. While for a resistor you can write that PR of T is equal to V square R of T divided by R, or I square R by of T into R. So you know all these equations. And also for a capacitor you can write the equation of capacitor as IT into VT, and then you can replace the current C. So current IC is always C dV by dt. So you can replace it here and apply the integral and you get half V square. So energy stored in a capacitor is half C V square. This is one important equation for the energy stored in capacitor, and we will see how it is used in CMOS circuits. So consider this inverter which is connected to a load capacitor CL. Okay, and what happens to the capacitor during charging? So during charging period, when the PMOS is on, the current flows in the capacitor and the capacitor stores half CL into VDD square. But at that time, the energy that the supply voltage delivers, or EVDT, if you put all the values, is CL VDD square. What this means that during the charging period, okay, so this is our charging path, what happens is that half Cl VDD square, this is dissipated in PMOS, while half Cl VDD square is stored. So the total energy delivered by the supply voltage, half of it is dissipated as this is dissipated as heat, while half of it is stored. Okay, and what happens during the discharge period? So let's say during the discharge cycle, this is the discharge cycle. What happens in the discharge cycle? All the half Cl VDD square, this energy is dissipated across the NMOS to ground. You can see that during the discharge period, no energy is drawn from the supply VDD. Okay, so during the discharge period, it is dissipated across the NMOS and dumped to the ground. So this is like the whole operation using graphics. So if you consider the first column, this is our first column, we have Vn here and V out here, and on this axis we have time in nanosecond. So you see that the input is 1, but then at 0.3 it goes down to 0, and then 0.6 it goes up. So this is the input to the inverter, and you see the output is opposite. So it goes up, because this is an inverter, it goes up at 0.3 and it starts to go down around 0.4 with some delay. So this is our input versus output curves. In the second column, you see here we have IP. So this is the curve for IP. This is IN, current through the NMOS, and this is IC, current through the capacitor. So you see that when the input goes down, so here the Vn is equal to 0, so which means that the PMOS is on. So that's why the PMOS currents goes up to the saturation point, and then when the capacitor Cl is charged, then fully charged, then from that point the VGS minus Vt, because of that it drops and it goes to the linear region. So this is the current of PMOS. This is the current of NMOS. So this happens when Vn is equal to 1, because the NMOS is only conducting when the capacitor is discharging. So this is the current flowing in the NMOS due to discharge of capacitor, and this is IC. So ICs, here it is written IC is basically IP minus IN. Okay, so basically you just subtract these two curves. So it is 1 here because of this, and it is negative here because of this. This is the capacitor current. In the third column we have the power in PMOS, power in NMOS, power in capacitor, and power delivered by VDD. So you see that the power is following a curve that is similar to the current. Okay, so here it translates to this, it translates to this, and this one translates to this. They are all multiplied with V out, and you see the supply current is the product of IP. You see here IP is used because the power is drawn from the supply voltage only when the PMOS is on. When the NMOS is on, no power is supplied by the VDD. So all the power supplied is in the charging cycle. On this side we have the energy stored in the capacitor, and on this second one we have the energy delivered by the supply voltage. Again you see that the supply energy saturates. So this is all the energy. Okay, what is mean by all the energy? It means the energy in discharge plus energy so you can say like this, that all the energy means the half C VDD square that is dissipated in PMOS plus half CL VDD square that is stored. So it is the sum of that all energy. Now coming to the switching power. So imagine this scenario where you have the inverter which is connected to a load, and you have this frequency of switching. So in digital circuits the signal go up and down in a 0-1 fashion, so giving you this pulse. So we are interested in what is the energy consumption during switching. So again the same formula we apply, then this VDD is a constant, so it goes out. Then you apply the integral, and again ID, because it is the current in the capacitor, so it is CdV by dt. Okay, so when you put this and you integrate, solve the integral, you get T C VDD. Why this comes into the equation? Because if you are considering 1, then you don't need it. But if you are considering when the frequency is 1, we don't need it. But when the frequency is more than 1, then you need to include this into the equation to account for multiple transitions. So the P switching is C VDD square F switching. Remember, this is the formula for the dynamic power consumption. So the final formula was this: P switching is alpha times C times VDD square times F. Now where does the alpha come from? So the alpha is basically the activity factor, and it basically tells us the transitions of our data signals. So how fast so one is the clock signal, which is our reference signal, and then we have a lot of data signals in our circuits. So alpha basically is related to the data signals. So what we say is that the switching frequency is alpha times F. So this is our clock frequency, and this is our activity factor, okay, and this is our switching frequency. So the final so we can say like this, that this equation is C VDD square FSW, because FSW is this thing, okay. So this is our final equation for dynamic power consumption. Now during the switching there is a point in time where both the NMOS and PMOS are 1 for a very, very short amount of time. So imagine you are flipping your input to the inverter. So your inverter input is Vn, and you are changing this to, let's say, 1. So there is a moment in time when both the PMOS and NMOS are momentarily 1. So this means that when both the so this is our PMOS and this is our NMOS, when both are 1, then there will be a short circuit. So there will be a short circuit to ground, okay, and there will be a flow of current. So this is called short circuit current. Normally this is and power will be consumed in this scenario, but normally less than 10% of the dynamic power is due to the short circuit current. So we can say that the total dynamic power, the total power dissipated during switching, total power consumed during switching is the dynamic power consumption plus this is the total power consumption, which is dynamic plus static, okay. But then dynamic power consumption, we have two factors. One is due to switching, and the other is due to short circuit current, okay. So but we already said that this is less than 10% of dynamic power, okay. So you can say the dominant factor is, this is the dominant factor, the switching power. Then the other one is static power consumption, which is this one, and there are so many factors. So this is due to the subthreshold leakage. So the current can leak into the body of transistor, current can leak into the gate. So ideally the gate should not draw any current, but it can. In the latest nanometer technologies, then there are junctions, for example the source drain junction and the source body junction, the drain body junctions. These are different junctions which can which are in some of the cases reverse bias, and they should not draw any current, but they can draw. And then there is this contention current. So there are so many sources of static current, and they are normally related to the physics of transistors not working according to the intended operation. So, but this is inevitable as we are reducing the size of transistors. The static power consumption is on the rise. So let's come to an example, which is the dynamic power consumption. So we have a 1 billion transistor chip, and those are typical numbers of transistors these days. And out of these 1 billion transistors, 50 million are so we have 1 billion transistors. Out of these transistors, 50 million are for logic and 950 million for memory. Okay, and then these transistors have a width of 12 lambda and alpha activity factor of 0.1. On the other side, these transistors have a factor of 4 lambda and activity factor of 0.02. Now note that the transistors used for memory are smaller but huge in number. So this is a typical case that if you take a chip, more than 50% of the area of the chip will be memory. So it may be a level 1 cache or maybe level 1, level 2 cache. Okay, so they are on the chip, so a huge amount of area is occupied by the memory subsystem. And then we have 1 volt as our supply voltage, and we have 65 nanometer process, and then we have the capacitance. So we have 1 femtofarad per micrometer as our gate capacitance and 0.8 femtofarad per micrometer as our diffusion capacitance. So diffusion capacitance are the capacitances created between when you dope regions. So for example CD or CS, these are diffusion capacitances. So the question is estimate dynamic power consumption at 1 gigahertz of frequency. Neglect wire capacitances and short circuit current. So we already have seen that the short circuit is less than 10% of the dynamic of the switching of the dynamic power consumption. So we can, and also we have not went into the detail, but wires have also capacitances, so we are told to neglect those capacitances. So okay, there is a mistake in this slide. this is not 65 nanometer, this is 25 nanometer. Okay, so note, not 65 nanometer but 25 nanometer. Okay, so first we calculate, we know that the dynamic power is alpha C V square F. So let me check. Alpha C V square F. So alpha C V square F. Okay, so let's first calculate the total capacitances. So this is the capacitances for logic, and we said that we have 50 million logic transistors, and each transistor has width of 12 lambda, and then these transistors are manufactured in 25 nanometer process. So this is 25 nanometer process, and then we have the total capacitance of transistor. So we were told that the total that the gate capacitance was 1 femtofarad per micrometer plus 0.8 femtofarad per micrometer for diffusion capacitance. So this is gate, and this was the diffusion capacitance. So we have to add those two up, and we get 1.8 femtofarad per micrometer. So when you multiply all these, you get 27 nanofarad. Then we can calculate for memory, which was 950 million transistor. Each transistor has a width of W. This is our 25 nanometer process. This is our CG and CD. So overall we have 171 nanofarad as our total memory capacitance. Now we can write, for example, this equations, which is alpha logic times C logic plus alpha memory times C memory into VDD square into F. So these two terms are here. Alpha logic was given in the previous slide. These two terms are here. This is here and this is here. So we get the total dynamic power of 6.1 watt. So you see, it's not very difficult to solve these numericals. Now let's come to the point of how to reduce the dynamic power consumption. Because why it's important? It's very important because battery powered mobile applications, so your laptops, your cell phones, all these things are powered by batteries, and the dynamic power is a factor that contributes to the drainage of battery. So when you have a huge dynamic power consumption, your battery will be drained very quickly. Now this is, you can say, on the mobile side, okay, mobile application side. but also on the server side. So imagine you have a huge data center. For example, it can be a data center of Google, where there are a huge racks of computer. Again, the huge dynamic consumption means huge cost of electricity. Okay, because not only they consume more electricity, but the data center requires air conditioning to cool it down. So also the cost of air conditioning will add up. So dynamic power consumption is a factor to consider, not only in mobile applications but also in server applications. Now, how can we minimize the dynamic power? We have the first factor is the activity factor. So basically it is the you can say the transitions of data signals. Now, the transition of data signals is something that comes from your let's say algorithm or application. Okay, so normally this is not in your you can say you don't want to change the algorithm, so not good to reduce dynamic power. It doesn't give you the control to reduce the dynamic power, because you cannot, okay, you can change maybe algorithm 1 to algorithm 2, and the algorithm 2 may have let's say less data transitions than algorithm 1. Okay, so imagine if you are computing the factorial of a number, so you can put an algorithm with for loops. This may be algorithm 1, and you can put an algorithm with recursion, so this may be algorithm 2. So maybe the recursion one has less data transitions than the algorithm 1. But from a perspective of circuit designer, this is not what circuit designers do. This is what software developers do. So we say that the activity factor is coming from the software world and it's not in our control. Okay. Then the capacitances are again something that is coming from the manufacturing process, from all the layouts and all these things. So that can be controlled, but they are very difficult to control. Then we have the supply voltage. This is a very good candidate, because you see that the power is proportional to VDD square. So if you reduce the voltage, the power consumption will go down by a square root of 2. So that's very good. And then we have the frequency, which has a linear relationship with the dynamic power consumption. And I told you before, if you remember from the midterm, that this is why we went multi-core. So why not just Intel produce a microprocessor with 10 gigahertz frequency? The issue is this one, that when you increase frequency, the switching increases and dynamic power consumption increases. So the solution was to go multi-core, to use multiple cores at a lower frequency than a single core with higher frequency. So power consumption is really driving the design of semiconductor industries these days. Okay, so activity factor estimation. We can say that, let's say that let Pi be the probability that a node I is 1, so that the you know that probability always ranges from 0 to 1. So the probability, this is probability of node equal 1. The probability of node equal 0 is 1 minus Pi. And then we have another important equation, that the switching activity is basically the probability of a node being 1 multiplied by the probability of a node being 0. So if we assume a completely random data in which the probability, let's say 50% of the time the output is 1 and 50% of the time the output is 0, then alpha is equal to 1 by 2 into 1 minus 1 by 2, which is again 1 by 2, so it is 1 by 4, which is 0.25. So but data is not often completely random. For example, if you are using a bank account, and you have a 64-bit word, the upper bits are 0. So this is an example of data where the most significant bits are 0 and the least significant bits will frequently change. Okay, so it is an example that data is not often random, but some bits change frequently and some bits do not change frequently. Let's go to the typical switching probabilities of some of the gates. So for an 2-input AND gate, if this is our 2-input AND gate and this is our input A and this is our input B and this is our output Y, then the probability of A being high, probability of B being high is related to the probability of A being high, as Py is equal to Pa Pb. So the chance or the probability that A is high multiplied by the probability of B being high is gives you the probability of output being high. For a 3-input AND gates, Pa Pb minus Pc. For a OR gate, it is 1 minus Pa bar Pb bar. For NAND, 1 minus Pa Pb. For NOR, Pa bar Pb bar. For XOR. So this table is what you have to remember, or you will be given when you are asked to solve these problems. So consider a 4-input AND gate which is implemented in 2 levels. And this is level 1, this is level 2. The first levels are 2-input ANDs and the second level is a 2-input OR gate. Okay, so estimate the activity factor at each node if the input has a probability of 0.5. We can say that Pa is 0.5, Pb is 0.5, Pc is 0.5, Pd is 0.5. So what is the probability that the output of, let me call this NAND 1, NAND 2 and this is OR 1. So let's calculate the probability that the output of NAND 1 is 1. So if we go back to the table, for NAND it is 1 minus PA PB. So 1 minus PA PB. Okay, so it will give us 1 minus 1 by 2 into 1 by 2, which is 3 by 4. Okay, so what is alpha N1? It is Pi bar Pi. So in this case we have our probability of output node being high is 1 minus 3 by 4 into 3 by 4, which is 1 by 4 into 3 by 4 is equal to 3 by 16. So this is the same for NAND 1 and for NAND 2. The probability of output being high is 3 by 4 and the switching activity is 3 by 16. Let's come to OR1, which is probability of O1. This is a OR gate, and for OR gate we have 1 minus PA bar PB bar. Okay, so PO1 is equal to 1 minus what is PA? PA is 1 minus 3 by 4. PB is 1 minus 3 by 4. P01 is equal to 1 minus 1 by 4 into 1 by 4 is P01 is equal to 1 minus 1 by 16, or it is equal to 15 by 16, and alpha is Pi bar Pi, so it is equal to 1 minus 1 by 16 into 15 by 16. So alpha O1 is basically 1 by 16 into 15 by 16 is equal to 15 by 256. Okay, now note that in the book this probability is 1 by 16, but according to our calculation it is 15 by 16. So I think this is a mistake. Okay, you can also verify this with your own calculation. Okay, let's go to another example. This is also a part of example 5.2. So in this we have A, B, we have a NAND gate, then we have this NOT gate, then we have another AND gate, then we have another NOT gate, then we have another NAND and another NOT. So this is for Z, and this is C, and this is D. Again, the probability PA, PB, PC, they are all PA, PB, PC, PD, they are all 0.5 to start with. Okay, so what is the solution? The solution is that the probability here is, this is a NAND gate. So for NAND gate we have for NAND gate we have 1 minus PA PB. So remember this, because we only have NAND gates here, so we can write the probability here as 1 minus 1 by 2 into 1 by 2, which is 3 by 4. And similarly, alpha is 3 by 4 into 1 by 4, which is 3 by 16. Then moving to the NOT gate. NOT gate probability is the opposite. So if this is the probability of this node to be high, then the probability of the output of NOT gate to be high is 1 minus 3 by 4, which is 1 by 4. Okay, and the switching activity, so this is P, this is alpha, this is P here. The alpha will remain the same because we have 1 by 4. So 1 by 4 into 1 minus 1 by 4 is again 3 by 16. And the probability here is again 1 minus 1 by 4 from this one, from the NOT gate, and 1 by 2 from the C input. So we will get 1 by 1 minus 8 is equal to 7 by 8, and alpha is equal to 7 by 8 into 1 minus 7 by 8 equal to 7 by 64. And then this node is again a NOT gate, so the probability will be 1 minus 7 by 8 is equal to 1 by 8, and the alpha will be same as 7 by 64. For this node we have P1 minus 1 by 8 into D, which is 1 by 2. So this is 1 by 1 minus 16 is basically equal to 15 by 16 is our probability, and alpha is 15 by 16 into 1 minus 15 by 16, which is equal to 15 by 256. And for this node it is so the node before is 15 by 16, so it will be 1 minus 15 by 16 is 1 by 16, and alpha is the same as 15 by 256. So this was for examples. Now, what is clock gating? If we want to reduce the activity factor, because the dynamic power was alpha c v square f. So if we want to reduce alpha, which is the switching activity of data signals, we can use a scheme like this. So this is our clock gating logic, and this is our circuit. So here it is shown as a simple register, but imagine this can be a whole ALU or a whole some other part of your circuit. So you see that the clock signal is driven by two things. One is your clock, which is coming from the crystal, and the other input is coming from user control logic. So when the user control logic is 1, the clock is considered to be passed, and when it is 0, the clock is 0. So when the clock is 0, there is no switching and your circuit consumes no power. Then again, if we write the dynamic alpha c v square f, the second thing that consider is reduce the capacitance. So there are two kinds of capacitances. One that arises from the gates, you can reduce it by using fewer stages of logic, or you can use smaller gates. Okay, and then the gate, the capacitance that the second capacitance, that is wire capacitance. Until now we have considered that wires are ideal, but actually they are not. In fact, there is a whole chapter on the wire modeling, and that is chapter number 6. I don't think that we will have time enough to go through chapter number 6, but there is a whole treatment of how to extract the capacitances from your wires and what are the models for that. But in our discussion, we have kept it that the wires are ideal. Then the other, so again, if the dynamic power is considered, is alpha c v square f. So we can control these two, voltage and frequency, and sometimes this is called dynamic voltage frequency. You can, if you control both simultaneously, it is called dynamic voltage frequency scaling, or DVFS. So you have, for example, here is DVS, which is only controlling the voltage, but according to frequency. So you have your logic here, and there is some kind of controller which passes sort of variable VDD. So VDD is not constant, it scales it down and up according to the needs, so that your power consumption is controlled. So these are some of the schemes that you can employ to control. Okay, so let's go through an example to calculate the static power consumption. This is the same example before, for which we have calculated the dynamic power consumption, but this time we will calculate static power consumption. This is in fact example 5.4. So again, we have the 1 billion transistors, in which 50 million were logic and 950 million were memory transistors. The memory transistors has a width of 4 lambda. The logic transistors have a width of 12 lambda. Now there are some extra details. So estimate the static power consumption such that the normal threshold voltage is 100 nanoampere per micrometer of the width, and a high threshold voltage is 10 nanometer per threshold. So these are two different kinds of transistors are used. One has a normal threshold voltage and the other has a higher threshold voltage. Okay, so higher threshold voltage are used in memory. Okay, so regarding to speed, when the threshold voltage is higher, they have lower speed or higher delay, and the normal VT are fast. So all the memory, they use what are called high VT, but 95% and 95% of logic gates. So 95%, if I take the logic one, so 50 million logic, 95% are high VT and 5% are normal VT. So these are the fast transistors. They are used in what is called critical path. So when we go to the combinational logic chapter, we will see what is critical path. So they are used in critical path to speed up your circuit. Additionally, the gate leakage is 5 nanometer per micrometer and the junction leakage is negligible. So we have to calculate the normal the width for normal VT. So this is our 50 million logic gates. Each one of the logic gate has a width of 12 lambda. This is our 25 nanometer process, and only 5% of them, 5% are normal VT. This is given. So we get this value 0.75 multiplied by 10 raised to the power 6 micrometer. Then we can calculate for the high VT. Remember, the high VT are used in 95% of the logic. So this is 95% of the logic, and all the memory uses. So 50 million multiplied by 12 lambda multiplied by 95% plus 950 million multiplied by 4 lambda for the memory multiplied by the process technology. So we get this value. Now the leakage current in the substrate I sub is basically the width of normal transistor, which we have calculated in 1 multiplied by 100 nanometer per micrometer. This is given, plus the width of high threshold transistors, which is given in 2 multiplied by 10 nanometer per micro ampere divided by 2. Now this division by 2 is that because only half of the width of transistors contribute to leakage. So that's why it has to be divided by 2. Only half of the width of a transistor contributes to the leakage current. Similarly, we can find the gate leakage current. So we already found the width from equation 1 and 2, and the leakage gate current is given by this. So we get the total leakage gate current this. We add up the I gate plus I subtract, multiply with our voltage, and we get the total static power consumption in our chip. So if you remember the dynamic power, it was 6.1 watt. If you compare it to the static power, it is less than 1 watt. Okay, but still this is a wastage, because the static power is consumed when your chip is not performing any useful work. So one way to reduce the static power is to use power gating. Reduce static power, and this is how your laptop works. So remember, you in your laptops you have a sleep option. So when you put it to sleep, the circuitry is turned off, and how it is done is that you have a bunch of transistors, in this case PMOS. They are connected to VDD supply, and when you put the, for example, the sleep to 1, all these transistors are turned off, and your circuit, this is your circuit, is actually isolated from the supply voltage. Also note that at the output there is an AND gate with the sleep signal. So if sleep is 0, the output is not isolated. When the sleep is 1, the output is isolated. So this kind of arrangement can be used to completely isolate the circuit and actually isolate it from the power supply. So in this way we can reduce the static power consumption. This is all for chapter number 5. We have covered some selective sections and topics, but this is enough for our needs. You should know how to calculate the activity factors in a circuit. You should be able to calculate the dynamic power consumption, and you should be able to calculate the static power consumption. That's all what we need in this course.